How does quantum mechanics view space? Have you ever wondered how quantum mechanics changes our understanding of space? It turns out, this field of science challenges the traditional views that we have held for centuries. Traditionally, we think of space as a three-dimensional area where objects exist and events happen. But quantum mechanics paints a different picture. At its core, quantum mechanics uses a mathematical concept called the wave function to describe physical systems. This wave function does not just exist in our familiar three-dimensional space. Instead, it often exists in a higher dimensional configuration space. This means it represents all possible states of a system at once, rather than just their positions in physical space. This raises interesting questions about whether our usual three-dimensional space is the fundamental reality. From the viewpoint of ontology, which studies what exists, quantum mechanics suggests that our familiar three-dimensional space might not be the most basic framework of reality. Some interpretations indicate that particles and fields, which we consider real, do exist in three-dimensional space but are described by quantum states. These states can show non-local correlations, meaning parts of a system can be connected instantly, regardless of the distance between them. This challenges the classical idea that space separates objects independently. Other philosophical views propose a primitive ontology. This idea suggests that the basic building blocks of reality are entities located in three-dimensional space or four-dimensional spacetime. In this view, the wave function is not a physical object itself but a tool to describe how these localized entities behave and interact. This perspective helps maintain a classical view of space while still accounting for quantum phenomena. Some interpretations, like the many worlds interpretation, expand the concept of space even further. They suggest that space is part of a much larger structure where many parallel worlds exist simultaneously in the same three-dimensional space and time. This idea broadens the ontology of space to include multiple realities that branch out from one another. These philosophical discussions significantly influence how scientists and philosophers understand phenomena like entanglement. In entanglement, particles show correlations that cannot be explained by signals traveling through space at or below the speed of light. This challenges the classical notion of locality and suggests that space in quantum mechanics is not just a passive container. Instead, it plays an active role in the structure of reality. In essence, quantum mechanics presents space as more than just a static, three-dimensional container. It suggests a complex, possibly high-dimensional or non-local structure that underlies physical phenomena. This invites us to rethink the ontological status of space, balancing our classical intuitions with the new features revealed by quantum theory.